Two tools that can help us improve the quality of our contracts are static analysis and linting. Technically, linting is also a static analysis tool, but by linting we mean a much lighter version of static analysis that can actually run while you type. It works with incomplete contracts. It is conservative, so it doesn't show all the errors that are possible, but it shows some of them. And it's only available in the Marlowe editor and the Blockly editor. In the Marlowe editor, it shows us yellow squiggly lines that appear under the code in the places where there are problems that have been found. Unlike static analysis, linting is able to highlight several problems at the same time, and it can also make some suggestions as ways to simplify the code that you write. On the other hand, static analysis is exhaustive. It checks every possibility. It has to be triggered manually by you. It won't happen automatically. And it needs a complete contract. It cannot have holes. And if it has parameters, you will be prompted to give values to those parameters. Unlike the linting, it supports all the editors and it only shows you the first error it finds at the time. If you want to find another error, you'll need to fix the first one first. And it also doesn't make suggestions. Linting gives this kind of hints. It tells you about non-positive payments and deposits. It tells you about timeouts that are not increasing with respect to the previous timeout. It tells you about unreachable code to some extent, about identifiers that you have used before defining them, about shadowing with LEDs, about values and observations that can be simplified, and also about partial payments, payments that don't have enough money to be satisfied to some extent. On the other hand, static analysis has three modes: warnings, unreachable code, and explicit refunds. And warnings will tell you about payments which are impossible, again, partial payments, non-positive deposits or payments, that is, the ones that are either negative or zero, and also about assertions. And we will look into this in a moment. This contract, for example, has two timeouts which are the same. And we can see that the linting is pointing us that timeouts should always increase in value. So that's one thing that the linting helps. In this other contract, we have a deposit which is negative, and the linting will also tell us. So we can fix the constant to be positive, and then linting will say nothing. But afterwards, if we add another construct which is pay, and it's negative, it also tells us. The contract can make a non-positive payment. If we make the same payment as the deposit, then everything will work. But the moment we add one extra ADA, then we get another linting. The contract makes a payment of 101, while there's only 100. And like we said, another possibility is that linting makes suggestions about how to simplify the contract. So here, for example, I'm writing the constant as a mathematical expression, and the linting will indeed suggest us that we simplify it into a single constant, because that's equivalent. If we click the quick fix and we click simplify value, then it will do it automatically for us. Of course, static analysis will also do this, and like Lars pointed out, it will tell us exactly the sequence that you have to follow in order to find the error, and it will tell you the error you will find. Let's see now how can we use the assert construct. For that, let's open the escrow contract in Blockly. You can see that at this point there is a payment between accounts from the account of the seller to the buyer. So we may want to make sure that the accounts are in the state that we want them to stay. So we can do that by using an assert construct and writing our assumption in the observation of the assert, like this. This assertion says that the amount of ADA in the account of the buyer must equal the price parameter. Because we have parameters in the contract, before running static analysis, we are asked to fill them in. By default, the timeouts or deadlines are all initialized to be 5-minute increments from the current time. And we need to set the value parameters manually. So let's set it to 108 in this case. In this case, we can see our assertion was correct and the analysis passes. But we could have written the seller account instead, and then the analysis would have found that the assertion indeed fails for a particular scenario. And the instructions on how to get to that scenario is indeed written here step by step, like we can see. Just for fun and to show the power of the static analysis, let me show you a ridiculous contract. Consider the following mathematical puzzle. Imagine that you are tasked to find 4 numbers A, B, C, and D such that A plus B equals 80, A plus C equals 130, B plus D equals 80, and C minus D equals 60. It's actually possible to write a Marlowe contract that has an assertion such that the assertion will only fail if there is a solution to this problem. Let's have a look. So we can see we have made 4 choices in a sequence, one for A between minus 100 and 100, one for B, one for C, one for D, and then we have an assertion which says not A plus B equals 8, and C plus D equals 60, and A plus C equals 130, and B plus D equals 80. So if we now run the static analysis, it will come up with an example, and it will tell us exactly which choices we need to make for the assertion to fail. So that would be the solution to the problem. Of course, this is not a convenient contract, but it shows the power of the static analysis. Lars already showed how to use the reachability analysis, but just another example, if in escrow we change one of the choices to match a previous choice in the same when, then that choice becomes unreachable because the choice before will always be picked. And we can see that in reachability analysis. So we can see that analysis for warnings still passes, but if we launch the analysis for reachability, we will see one counterexample, which exactly points you to the case that we just modified. So we can see that it says it's the first case in the first when, the second case in the second when, then there is a payment, and then the second case in the third when, which is the one we modified, it says it's unreachable. And Lars also briefly mentioned the analysis for refund, but let's have a look at how examples take advantage of this analysis in particular. So we can see that if we pick the escrow contract, it pretty much every clause it has implicit refunds. And that is because we want the contract to be as concise as possible, because the larger the contract is, the more it's going to occupy on chain and the more money is going to be necessary to be paid in order to run the contract. But the way we design the contract is using either Haskell or JavaScript embedding in a way that we parameterize whether the refunds are implicit or not. So you can see that if you load a Haskell or JavaScript example, it has this variable which is called explicit refunds, and it is set to false by default, because that is what produces the shortest code. But we can change it to true and recompile. And now we can run the refund analysis again, and we see that it passes with no implicit refunds. So that is the technique we use. We design the contract using explicit refunds so that we are sure that it does what we want it to do, and then we remove them in order to get a smaller contract. You can see the details in the implementation. Here in refund buyer and refund seller functions, we have explicit refunds that produces a pay, but if explicit refunds is not set, then we just produce close.